Suppose we have an object that we've never seen before. If we want to know what it looks like, we can just pick it up and rotate it. After turning it enough, without too much effort, we can figure out its general shape. This is easy for us because we have two eyes, two viewpoints that simultaneously view the object from very small angular separation. Our mind easily constructs our 3D view of the object from the pairs of 2D images that our eyes record. But what if we don't have two eyes, instead only one? Is it still possible to view an object in 3D? The answer is, yeah, it is possible, through the mathematical relations that are the foundations of tomography. Tomography is a set of powerful image reconstruction techniques that allow a 3D image of an object to be reconstructed from 2D scans of an object from several different angles. Electron tomography is a specific subset that relies on scans from TEM spectroscopy. Because of this, the technique is sometimes referred to as 3D TEM. Tomography has its roots in the relationship between the Radon and Fourier transforms. The Radon transform can be thought of as a set of projections into the 2D plane from all possible viewing angles. By taking several samples of these projections, we have the building blocks needed to create our 3D image. Thanks to the Fourier slice theorem, we can take the 2D Fourier transform of each of these projections and compile them into a 3D Fourier transform of the object that we would like to construct. We can then get the 3D spatial reconstruction by taking the inverse Fourier transform of this data. We can't just naively backproject our image because the resulting 3D image will be blurred. In order to remove this blurring, each projection is sent through a ramp filter and then backprojected in a process called filtered backprojection. The resulting image has a much higher resolution, though some slightly exaggerated edges due to the high-pass nature of the ramp filter. When dealing with visualizations of objects at the nanoscale, there are a lot of ways to measure attributes of a sample in order to create an image. The goal of electron tomography is to create a 3D image that represents the actual physical shape of the object. If we're recording 2D projections of the object, then we just need to record an image that shows us the projected density of the object. In other words, the shading of a pixel in the image linearly corresponds to the amount of material in front of that pixel. There are a couple ways to record images like this, but the most popular choice is annular dark field STEM. This technique is useful because there is little phase and diffraction contrast, and its transfer function acts as a low-pass filter, meaning that image edges are not exaggerated, which is great for 3D image reconstruction. Most importantly, the image recorded depends almost exclusively on the projected density of the object. However, there's a large drawback using this technique. Remember that we need to acquire a tilt series of images. We can do this by tilting the sample stage along some axis. To get a complete 3D reconstruction, we need to get samples from as many angles as possible. However, due to the physical limitations of the sample stage, we're only able to acquire samples from about a 120-degree sweep. There's a problem of a missing wedge in the Fourier domain. This problem is a huge issue when we're missing around 60 degrees of tilt. Large streaking and smearing artifacts occur that severely impact reconstruction efforts when we use standard backprojection techniques. The problem can be somewhat alleviated by introducing another axis of rotation. Now we instead get a problem of a missing cone instead of a missing wedge. However, this usually doesn't significantly increase the resolution or accuracy of reconstructed images, and so it usually isn't used. To help reduce these significant artifacts, several iterative methods have been devised. The general approach to these techniques is to realize that the missing wedge creates an underdetermined linear system. In addition, due to noise, this system is likely to be inconsistent, so the system of equations that need to be solved will instead be an optimization problem to minimize the residual of the system. A recent and very promising algorithm in the image reconstruction field is the total variation augmented Lagrangian alternating direction algorithm, or TVAL3, developed here at Rice University in 2012. TVAL3 performs better than many other recovery algorithms when presented with partial data and considerable noise, and so is a good contender for solving the missing wedge problem. However, there are still several tweaks that need to be made to the algorithm to increase its accuracy and efficiency. Overall, electron tomography is a very powerful tool. The record resolution attained by a tomography system is a linear 2.4 angstroms. Despite this, there is still plenty of potential for improvement of tomography imaging systems.